Hello everyone and welcome. In this video we're going to determine the generating function of the sequence formed by generalized harmonic numbers of order m. So it's going to be the sum as n goes from 1 to infinity of the nth harmonic number of order m times z to the n, where the nth harmonic number of order m is equal to the sum as k goes from 1 to n of 1 over k to the m, and m is a positive integer. Okay, let's get started. We're going to start with the convergence of our power series. So we know that the power series always converges at the center of the power series. Because it's a power series at 0, we're going to exclude the case where z is equal to 0. So we're going to assume that z is different from 0. Then we want to use the ratio test in order to find the radius of convergence. So we want to look at the limit of the modulus of the following ratio. So we have the n plus 1th harmonic number of order m times z to the n plus 1 divided by the nth harmonic number of order m times z to the n. And using the definition of the nth harmonic number, we can simplify this. Now, if we split the fraction, we get the following. As n goes to infinity, the nth harmonic number of order m is going to converge to zeta at m, where zeta is simply the Riemann zeta function. And 1 over n plus 1 to the m will tend to 0. Therefore, the whole thing is going to converge towards the modulus of z. And because we're using the ratio test, we want this ratio to be less than 1 in order to have convergence. So this tells us that the radius of convergence of the generating function is equal to 1. Okay, this is important. Now we want to introduce some notations. So we're going to denote by p of x the polynomial defined as the product of xi's as I goes from 1 to m, where x here is an m tuple formed by real numbers. We're going to denote by I in the interval from 0 to 1, the closing interval, and we're going to denote by I to the m, the I per cube, which is obtained by taking m copies of I as Cartesian products. Okay, so now we're going to denote by f sub m as the generating function we're trying to find. Okay, now the first thing we want to do here is express the nth harmonic number of order m as an integral. Okay, so we're going to compute the integral from over the I per cube im of 1 minus p of x to the n divided by 1 minus p of x dx. If we divide 1 minus p of x to the n by 1 minus p of x, we get the sum as k goes from 0 to n minus 1 of p of x to the k. And because we have a finite sum, this finite sum can go outside of the integral. And then, using the definition of p of x, we can write this integral as a product of integrals. Each of those factors are going to be equal. And they are all equal to the integral from 0 to 1 of t to the k dt. Okay, now all we have to do is compute the integral. So as we compute the integral, we get the sum as k goes from 0 to n minus 1 of t to the k plus 1 divided by k plus 1, which we're going to evaluate from 0 to 1, raised to the nth power. Okay, after simplifying, we get the sum as k goes from 0 to n minus 1 of 1 over k plus 1 to the m. And after rearranging the index here, we get the sum as k goes from 1 to n of 1 over k to the m. And this is precisely the nth harmonic number of order m. Okay, so we have an integral representation of our nth harmonic number of order m. Now we are going to plug that inside the generating function. So the generating function f sub m at z which by definition is the sum as n goes from 1 to infinity of the nth harmonic number of order m times z to the n, is now equal to the sum as n goes from 1 to infinity of the integral over the ip cube of 1 minus p of x to the n divided by 1 minus p of x dx times z to the n. Okay, the sum can go inside the integral. Okay, and then we're going to get the integral over the ip cube of 1 over 1 minus p of x times the sum as n goes from 1 to infinity of 1 minus p of x to the n times z to the n, and then dx. Now, the sum is simply the difference. Well, it's the sum of the difference of two geometric sequences. So we're going to have the following. After simplifying, we're going to get z over 1 minus z times p of x divided by 1 minus z times p of x. Okay, now we want to combine these two fractions. We combine these two fractions and we obtain z times 1 minus p of x divided by 1 minus z times 1 minus p of x times 1 minus z times p of x. Okay, we can simplify 1 minus p of x because it appears in the numerator and denominator. After simplifying and factoring z by 1 minus z, we get the following. So fm at z is equal to z over 1 minus z times integral over the ip cube of 1 over 1 minus z times p of x dx. Okay, now we want to expand this into a power series with respect to z, of course. In order to do that, we have to make sure that the product z times p of x is actually less than 1 in modulus. And this is actually the case because x is actually inside the ip cube, and we know that each xi is going to be less than 1. And z, we just saw that the radius of convergence of our generating function was 1, and it was convergent inside the open unit disk. So if we take the modulus of z times p of x, we know that it's going to be less than 1. Okay, so now we can actually expand this into a power series. So we're going to have z over 1 minus z times integral over the ip cube of the sum as n goes from 0 to infinity of z times p of x to the n dx. Okay, we can simplify, and using the dominating convergence theorem, we can actually take the sum outside of the integral. So if we take the sum outside of the integral, we get the following. So now z to the n is simply a constant with respect to x. So we can also take it outside. So by taking it outside, we get the following. Now again, we have the integral over the ip cube of p of x to the n. Well, p of x to the n is simply a product of xi's. So it's going to be the product of xi's to the n as I goes from 1 to m. So this integral is going to be the product of exactly m integrals, and each of those integrals are going to be equal to the integral from 0 to 1 of t to the n dt. So we're going to get the nth power of the integral from 0 to 1 of t to the n dt. Now, we just compute the integral now, and we get exactly that fm at z is equal to 1 over 1 minus z times the sum as n goes from 0 to infinity of z to the n plus 1 divided by n plus 1 to the m. Okay, now we're going to rearrange the terms by simply replacing n plus 1 with n. In that case, n is going to start from 1, not from 0. So we're going to get 1 over 1 minus z times the sum as n goes from 1 to infinity of z to the n divided by n to the m. Well, this sum is simply the polylogarithm of order m evaluated at z. So we're going to get the polylogarithm of order m evaluated at z divided by 1 minus z. Okay, so that's the generating function we were looking for. Now we want to look at a particular case. That will be when m is equal to 1. When m is equal to 1, the nth harmonic number, so the generalized harmonic number of order 1 is simply the nth harmonic number. So if we take the generating function, we're going to get simply the polylogarithm of order 1 evaluated at z divided by 1 minus z. But the polylogarithm of order 1 evaluated at z is simply negative the natural log of 1 minus z. And I think this is a good place to stop. Thank you for watching and see you next time. Bye.